3:47 a.m. on a Tuesday night in 1987, a physicist named Mitchell Feigenbaum flipped a light switch in his Princeton laboratory. Unknown to him, that simple action set in motion a cascade of events that would ripple through space and time, eventually influencing the gravitational dance between binary stars 4.2 million light-years away in the Andromeda Galaxy. This isn't science fiction. This is the terrifying reality of the butterfly effect, where the quantum uncertainty principle meets classical chaos theory. Tonight, we'll explore how every action you take, no matter how insignificant, sends invisible waves through the fabric of reality itself, potentially reshaping the cosmos in ways that would make even Einstein question the nature of causality. Chapter 1. The mathematician who discovered chaos in a coffee shop. In 1915, a brilliant German mathematician named Emmy Noether discovered something that would shake the foundations of physics forever. She proved that every symmetry in the universe corresponds to a conservation law. But here's what will blow your mind. When chaos theory emerged decades later, physicists realized that Noether's theorem doesn't just describe our reality, it might actually be the mathematical foundation that makes the butterfly effect possible. Emmy Noether was born into a world where women weren't allowed to attend university lectures. She had to sit in the back of classrooms, invisible and ignored, while male professors delivered their wisdom to paying male students. But mathematics called to her with a voice that couldn't be silenced by social conventions. In the quiet corners of coffee shops and the margins of borrowed textbooks, she began exploring patterns that would revolutionize how we understand the universe itself. What Noether discovered in those hidden mathematical explorations was breathtaking in its simplicity and terrifying in its implications. She proved that whenever the universe exhibits symmetry, something must be conserved. If the laws of physics are the same today as they were yesterday, then energy cannot be created or destroyed. If the laws work the same way in New York as they do in Tokyo, then momentum must be conserved. These weren't just mathematical curiosities, they were fundamental principles that govern every interaction in the cosmos. But here's where Noether's work becomes essential to understanding the butterfly effect. Her theorems revealed that the universe operates on perfect mathematical symmetries. Yet chaos theory would later show us that these same symmetrical systems can break down in completely unpredictable ways. The mathematical elegance that Noether discovered contains within it the seeds of its own beautiful destruction. Think about a perfect sphere rolling down a perfectly smooth hill. Noether's conservation laws tell us exactly how its energy transforms from potential to kinetic. The mathematics are clean, predictable, eternal. But add just one tiny pebble to that hill, one microscopic imperfection, and suddenly, the sphere's path becomes chaotic. It might veer left or right, bounce unpredictably, or even roll backward. The conservation laws still hold, but the system's behavior becomes impossible to predict. This is the profound paradox that Noether unknowingly discovered. The universe is governed by perfect mathematical laws, yet those same laws allow for infinite unpredictability. She had found the source code that makes chaos possible. Every conservation law, every symmetry principle, every mathematical constant that keeps the universe stable also creates the conditions where tiny causes can have massive effects. Noether's work revealed that reality operates like an incredibly sophisticated computer, program running on mathematical principles. But unlike the rigid programs we create, this cosmic software contains infinite flexibility. The same equations that ensure energy conservation also allow a butterfly's wings in Brazil to influence weather patterns in Texas. The same symmetries that keep electrons in their orbits also permit quantum uncertainties to cascade into macroscopic chaos. The tragedy is that Emmy Noether never lived to see chaos theory emerge in the 1960s. She died in 1935, decades before Edward Lorenz would discover sensitive dependence on initial conditions. She never knew that her elegant theorems about symmetry and conservation would become the mathematical foundation for understanding how unpredictability emerges from perfect order. but perhaps that's fitting. Notha herself was a living example of the butterfly effect. A woman working in the shadows of a male-dominated field, creating mathematical insights that would ripple through decades to fundamentally change how we understand reality. Her quiet work in coffee shops and borrowed lecture halls set in motion intellectual cascades that continue to transform physics, mathematics, and our understanding of causality itself. When modern physicists study chaotic systems, they rely on Noether's conservation laws to understand which quantities remain stable, even as everything else spirals into unpredictability. Energy is conserved, but its distribution becomes chaotic. Momentum is preserved, but its direction becomes impossible to predict. Her theorems provide the mathematical scaffolding that allows chaos to exist without destroying the fundamental structure of reality. The deeper truth that Noether discovered is that the universe is neither perfectly ordered nor completely random. It exists in a miraculous balance where mathematical laws create the possibility for infinite creativity. Her work showed us that reality is like a cosmic improvisation, where eternal principles provide the harmony while chaos supplies the melody. Every symmetry she discovered creates space for asymmetrical surprises. Every conservation law she proved enables unconservative innovations. This is why Noether's theorems are essential to understanding the butterfly effect. They reveal that the universe is constructed in such a way that tiny causes can have vast effects while still maintaining its fundamental coherence. The mathematical elegance she discovered doesn't prevent chaos. It makes chaos possible while ensuring that reality doesn't dissolve into complete randomness. As we prepare to explore how a light switch can influence distant stars, remember that we're building on foundations that Emmy Noether laid in coffee shops nearly a century ago. Her insights into symmetry and conservation reveal why the butterfly effect isn't a breakdown of natural law, but rather the most profound expression of how natural laws actually work. In the mathematical principles she discovered, we find not just the rules that govern reality, but the cosmic permission for every small action to participate in reshaping the infinite complexity of existence itself. Chapter 2. When Newton's clockwork universe shattered for nearly 2 centuries after Isaac Newton published his laws of motion and universal gravitation in 1687, the universe seemed like a perfectly predictable clockwork machine. Every planet followed its ordained path. Every comet returned on schedule. Every eclipse could be calculated centuries in advance with stunning accuracy. The mathematical elegance was so complete, so seemingly infallible, that scientists believed they had discovered the ultimate truth about reality itself. In 1814, the French physicist Pierre-Simon Laplace crystallized this worldview in what became known as the most arrogant statement in the history of science. He imagined a hypothetical being, now called Laplace's demon, that possessed complete knowledge of the present state of the universe. This supernatural intellect would know the exact position and momentum of every single particle in existence, from the tiniest atoms to the largest stars. If such a being could process all this information, Laplace declared, then the future would be as predictable as the past. Nothing would be uncertain. Everything would unfold according to mathematical destiny. Laplace wrote that for such an intellect, nothing would be uncertain, and the future as the past would be present to its eyes. This wasn't just scientific confidence, this was a declaration that the universe was fundamentally knowable, completely determined, utterly predictable. Free will became an illusion. Surprise became impossible. The future was already written in the language of mathematics, waiting only for sufficiently powerful minds to read its equations. But even as Laplace made his bold proclamation, cracks were already appearing in the foundation of this clockwork universe. Newton himself had encountered problems that refused to submit to his elegant equations. The motion of 2 bodies, like the Earth orbiting the Sun, could be solved with beautiful precision. But add just one more body, say the Moon, and the mathematics became impossibly complex. Newton called this the three-body problem, and it tormented him for years. Newton once told his friend Edmund Halley that thinking about the moon's motion made his head ache and kept him awake so often that he would think of it no more. Here was the greatest mathematical genius in history, the man who had unlocked the secrets of planetary motion and universal gravitation, admitting defeat against a problem involving just three objects. The clockwork universe already had broken gears, even if no one yet understood why. The deeper issue wasn't that Newton's mathematics were wrong, they were perfectly correct. The problem was that some systems, even when governed by simple and deterministic laws, produce behavior so complex that no mathematical solution exists. The three-body problem wasn't unsolvable because Newton lacked sufficient skill. It was unsolvable because the universe itself had built-in mathematical barriers to complete prediction. For 200 years after Newton, mathematicians and physicists tried to crack the three-body problem using increasingly sophisticated techniques. They invented new forms of calculus, developed powerful approximation methods, and created mathematical tools that pushed the boundaries of human knowledge. But the problem remained stubbornly resistant to analytical solution. Each attempt revealed new layers of complexity, new mathematical obstacles that seemed to multiply rather than diminish. Then, in the 1880s, a brilliant French mathematician named Henri Poincaré approached the three-body problem from an entirely different angle. Instead of trying to find exact solutions, he asked a more fundamental question: do exact solutions even exist? His investigation led him into uncharted mathematical territory, where he discovered something that would shatter the clockwork universe forever. Poincaré found that even the simplest gravitational systems could exhibit what he called sensitive dependence on initial conditions. Two planets starting from almost identical positions and velocities could end up following completely different orbital paths. The difference in their starting conditions could be smaller than the width of an atom, yet over time, their trajectories would diverge until they occupied entirely different regions of the solar system. This discovery was mathematically shocking and philosophically devastating. Poincaré had proven that deterministic systems could be fundamentally unpredictable. The equations governing planetary motion were perfectly precise, but the solutions to those equations could be impossibly chaotic. Laplace's demon, even with infinite computational power, could not predict the long-term behavior of something as simple as three gravitating bodies. But Poincaré's discovery went even deeper than unpredictability. He found that chaotic systems create incredibly complex geometric structures in what mathematicians call phase space. These structures, which we now call strange attractors, contain infinite detail compressed into finite regions. They are fractals before fractals were officially discovered, patterns that repeat at every scale, geometries that never quite repeat themselves, yet never escape their prescribed boundaries. Poincaré realized he was looking at a new kind of mathematics, one that described systems poised between order and chaos. These systems weren't random because they followed precise mathematical laws, but they weren't predictable either because tiny uncertainties grew exponentially over time. They existed in a mysterious middle ground where determinism and unpredictability coexisted in perfect mathematical harmony. The implications terrified the scientific establishment. If three-body systems were unpredictable, what about more complex systems like weather patterns or economic markets or biological ecosystems? If simple, gravitational interactions could produce chaos, what hope was there for understanding systems involving millions or billions of interacting components? The dream of a completely predictable universe began to crumble under the weight of mathematical proof. Poincaré's work revealed that the universe contains what we might call mathematical trapdoors, hidden complexities that emerge whenever multiple objects interact in seemingly simple ways. These trapdoors don't violate physical laws. They arise directly from those laws. The same equations that produce beautifully predictable planetary orbits also create chaotic regions where prediction becomes impossible. What makes this discovery even more profound is that Poincaré found chaos hiding inside the most fundamental interactions in nature. Gravitational attraction follows Newton's inverse square law with perfect mathematical precision. Yet when three or more objects interact gravitationally, this precise law generates chaotic behavior. The universe had built unpredictability into its most basic operating principles. Poincaré's investigation also revealed something beautiful about mathematical chaos. While individual trajectories became unpredictable, the overall structure of the system remained comprehensible. Chaotic systems create patterns, just not the kind of patterns that allow precise prediction. They generate geometric forms of stunning complexity and beauty, mathematical sculptures that exist in dimensions beyond ordinary visualization. This insight foreshadowed one of the most important discoveries about chaos: that unpredictable systems often possess deep underlying order. The order isn't the simple, repetitive kind that allows exact prediction. It's a more subtle, fractal kind of order that reveals itself through statistical patterns and geometric structures. Chaos and order aren't opposites. They're dance partners in the cosmic ballet of mathematical possibility. By the time Poincaré finished his investigation, the clockwork universe lay in ruins. But from those ruins emerged something far more interesting. A universe where mathematical laws create spaces for infinite creativity. Deterministic equations don't just allow unpredictability, they require it. The same mathematical principles that ensure planetary orbits remain stable also guarantee that complex systems will explore vast territories of possible behavior. Poincaré had glimpsed what would later become known as chaos theory, butterfly effects, and sensitive dependence on initial conditions. He saw, decades before anyone else, that the universe operates according to principles far more subtle and powerful than simple mechanical predictability. He discovered that reality is not a clockwork machine grinding through predetermined motions, but rather a vast improvisational system where mathematical laws provide the framework for endless creativity. The irony is that Poincaré's discovery didn't diminish the power of mathematics. It revealed mathematics to be far more magnificent than anyone had imagined. Instead of being limited to describing simple, predictable systems, mathematics could capture the full complexity of chaotic dynamics. The same mathematical language that described planetary orbits could also describe the emergence of unpredictability from deterministic laws. When we flip a light switch today and wonder how that action might influence distant stars, we're asking questions that Poincaré's work makes meaningful. He showed us that the universe is constructed in such a way that small causes can have large effects, that deterministic systems can be unpredictable, and that mathematical precision creates rather than eliminates the possibility for genuine surprise. The clockwork universe is dead, but the mathematical universe that replaced it is infinitely more beautiful and mysterious. Chapter 3: The Meteorologist Who Broke the Future. In the winter of 1961, a meteorologist named Edward Lorenz sat in front of a primitive computer at MIT, trying to solve one of humanity's oldest dreams: predicting the weather with perfect accuracy. His computer was a Royal McBee LGP-30, a machine roughly as powerful as a modern pocket calculator, yet it represented the cutting edge of computational technology. Lorenz had programmed it with 12 equations, representing the basic physics of atmospheric motion, temperature, pressure, humidity, wind velocity, and other variables that determine whether tomorrow brings sunshine or storms. The computer would churn through these calculations, printing out rows of 12 numbers that represented the state of Lorenz's simplified atmosphere at each moment in time. He could watch his mathematical weather evolve step by step, hour by hour, as columns of numbers scrolled past on continuous paper. It was tedious work, but Lorenz believed he was on the verge of revolutionizing meteorology. If he could perfect his equations, weather prediction might become as reliable as astronomical calculations. On one particular day in December, Lorenz decided to examine a specific weather sequence more closely. He had run a simulation earlier, and now he wanted to study the middle portion in greater detail. Instead of starting the calculation from the beginning, he took a shortcut. He looked at the printout from his previous run, found the numbers from halfway through, and typed them back into the computer as new starting conditions. This decision seemed perfectly reasonable. The numbers on the printout represent the exact state of his atmospheric model at that moment. Entering them as initial conditions should produce exactly the same weather sequence he had calculated before. Lorenz set the computer running, then walked down the hall to get a cup of coffee, leaving the machine to calculate what he expected would be an identical forecast. When he returned an hour later, Lorenz discovered something that would change science forever. The new weather sequence matched the original for about 2 months of simulated time. Then, something strange began to happen. The patterns started to diverge. What had been a mild winter storm in the original run became a raging blizzard in the new calculation. High-pressure systems appeared where low pressure had been before. Temperature patterns flipped completely. Within a few more months of simulated time, the two forecasts described entirely different weather systems. Lorenz's first thought was that the computer had malfunctioned. Perhaps a vacuum tube had burned out, or some electrical connection had failed. These primitive machines were notoriously unreliable, and computational errors were common. He checked every component, tested every circuit, and verified every equation. But the computer was working perfectly. The calculations were mathematically correct. So why were two identical starting conditions producing completely different weather? The answer lay hidden in a detail so trivial that Lorenz almost missed it entirely. His computer calculated with 6 decimal places of precision, storing numbers like 0.506127. But when the computer printed results, it rounded them to 3 decimal places to save space on the paper. So a number like 0.506127 would appear on the printout as simply 0.506. When Lorenz typed the printed numbers back into the computer, he unknowingly introduced tiny errors in the 4th decimal place. The difference between 0.506127 and 0.506000 amounts to roughly 1 part in 1,000. In weather terms, this is like the difference between a temperature of 20.0 degrees Celsius and 20.01 degrees Celsius. Such a minuscule variation should have had no meaningful impact on weather patterns. But that's not what happened. Instead, Lorenz watched in fascination as this microscopic difference grew larger with each calculation cycle. After a few simulated days, the tiny error had doubled. After a few more days, it doubled again. The mathematical amplification continued relentlessly, following what mathematicians call exponential growth. Small differences became medium differences became large differences, and large differences became completely different weather systems. This phenomenon, which Lorenz named sensitive dependence on initial conditions, revealed a shocking truth about the natural world. Deterministic systems, governed by precise mathematical laws, could be fundamentally unpredictable if their starting conditions contained even the tiniest uncertainties. The atmosphere wasn't chaotic because the physics was wrong or because the mathematics was inadequate. It was chaotic because chaos emerged naturally from the correct mathematical description of atmospheric dynamics. Lorenz realized he had discovered something that would revolutionize far more than meteorology. He had found evidence that the universe contained systems where present conditions determine future outcomes with perfect mathematical precision, yet those same systems make prediction impossible beyond relatively short time horizons. The barrier to long-term weather forecasting wasn't technological. It was fundamental to the nature of atmospheric dynamics itself. Driven by scientific curiosity, Lorenz began simplifying his atmospheric equations to understand the essential mechanism behind this strange behavior. He reduced his 12-equation weather model to just 3 equations representing a simplified slice of atmospheric convection. air heated at the bottom, cooled at the top, and allowed to circulate in 2 dimensions. This toy model eliminated most of the complexity of real weather while preserving the mathematical essence of fluid, dynamics. Even this drastically simplified system exhibited the same shocking behavior. Tiny changes in starting conditions led to completely different outcomes. 2 identical convection patterns, differing by less than 1 part in a million, would evolve into entirely different circulation systems within a short time. The sensitive dependence on initial conditions wasn't an artifact of atmospheric complexity. It was a fundamental property of the mathematical equations describing fluid motion. Lorenz's 3-equation model produced something even more remarkable than unpredictability. When he plotted the system's behavior in 3-dimensional space, with each equation represented by 1 coordinate axis, the chaotic motion traced out a beautiful geometric structure. The system's trajectory never repeated exactly, yet it remained confined within a specific region of mathematical space. The resulting pattern looked mysteriously like a butterfly with outstretched wings. This discovery led Lorenz to coin the term that would capture the public imagination, the butterfly effect. In 1972, he gave a lecture to the American Association for the Advancement of Science with the provocative title, Predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The metaphor was perfect. Something as delicate as a butterfly's wing movement could, through the mathematical amplification of atmospheric chaos, eventually influence weather patterns on the other side of the planet. But Lorenz's butterfly effect revealed something far more profound than just weather unpredictability. He had discovered that deterministic chaos exists throughout nature. Any system governed by nonlinear equations, where small changes can produce proportionally larger effects, becomes potentially chaotic. This includes biological ecosystems, economic markets, population dynamics, chemical reactions, and even the orbital mechanics of planetary systems. The implications were staggering. Laplace's demon, that hypothetical being with perfect knowledge of initial conditions, could not predict the long-term behavior of chaotic systems, no matter how powerful its computational abilities. Even with infinite precision in measuring starting conditions, quantum mechanical uncertainty would introduce tiny errors that chaos would amplify into macroscopic unpredictability. The dream of perfect prediction was mathematically impossible. Lorenz's work also revealed why traditional scientific approaches had missed chaos for so long. Most laboratory experiments and theoretical studies focused on systems near equilibrium, where small perturbations produce small effects. Linear systems, where doubling the input doubles the output, dominate introductory physics and chemistry courses. But the real world is filled with nonlinear systems, where doubling the input might quadruple the output, or halve it, or trigger completely different behavior altogether. Weather. Prediction became the first practical application of chaos theory. Meteorologists abandoned the dream of precise long-term forecasts in favor of probabilistic ensemble predictions. Instead of calculating one future, they calculate many possible futures based on slightly different starting conditions. Modern weather models run dozens of simulations simultaneously, each beginning with tiny variations in initial atmospheric measurements. This ensemble approach revealed another crucial insight about chaos. While individual trajectories are unpredictable, statistical properties often remain stable. We cannot predict exactly when or where a particular thunderstorm will form, but we can estimate the probability of thunderstorms in a given region. Chaos destroys precise prediction, but preserves statistical forecasting. Lorenz's discovery transformed our understanding of natural limits. The barrier to long-term weather prediction isn't insufficient data or inadequate computers. It's the mathematical structure of atmospheric dynamics itself. No amount of technological advancement can overcome the fundamental impossibility of measuring initial conditions with infinite precision. Chaos imposes absolute limits on predictability that no scientific progress can circumvent. Yet within these limits, Lorentz found extraordinary beauty. Chaotic systems create geometric structures of infinite complexity, patterns that never repeat yet never escape their prescribed boundaries. The butterfly attractor he discovered contains infinite detail at every scale, like a mathematical fractal that reveals new intricacies no matter how closely you examine it. Chaos doesn't destroy order, it creates new kinds of order that transcend simple repetition. When Edward Lorenz walked down that hallway for a cup of coffee in 1961, he set in motion a revolution that would reshape science, mathematics, and philosophy. His accidental discovery of sensitive dependence on initial conditions revealed that we live in a universe where deterministic laws create space for infinite unpredictability. The butterfly effect isn't a breakdown of natural order, it's the most profound expression of how natural order actually works, allowing tiny causes to cascade through space and time, potentially reshaping reality itself in ways that even the most powerful computers cannot foresee. Chapter 4: The Strange Geometry of Chaos. When Edward Lorenz first glimpsed the butterfly-shaped pattern emerging from his weather equations, he was looking at something that shouldn't exist, according to traditional mathematics. Here was a geometric object that contained infinite complexity within finite boundaries, a structure that never repeated itself yet never escaped its prescribed limits. What Lorenz had discovered was a strange attractor, a mathematical entity that would revolutionize our understanding of how order and chaos dance together in the fabric of reality itself. To understand the profound strangeness of what Lorenz found, we need to explore the concept of phase space, a mathematical realm where every possible state of a system can be represented as a single point. Imagine trying to capture the complete behavior of a simple pendulum in one comprehensive picture. You might start with a graph showing position over time, or velocity over time, but these only reveal fragments of the pendulum's story. Phase space offers something far more powerful, a two-dimensional map, where the horizontal axis represents the pendulum's position and the vertical axis represents its velocity. In this phase space representation, every possible condition of the pendulum corresponds to exactly one point. A pendulum hanging motionless at the bottom appears as a dot at the center, where both position and velocity equals 0. A pendulum swinging back and forth traces out a closed loop, moving fastest at the bottom where its position is 0, but its velocity is maximum, and slowest at the extremes where its position is maximum, but its velocity momentarily becomes 0. What makes phase space so remarkable is that the curves representing different motions never cross. This isn't just a mathematical convenience, it reflects a fundamental truth about deterministic systems. Each point in phase space represents a complete description of the system's state, and that state has only one possible future. If two curves crossed, it would mean the same initial condition could lead to different outcomes, violating the deterministic nature of classical physics. For simple systems like pendulums or planetary orbits, phase space portraits reveal beautiful, predictable patterns. A pendulum with friction spirals inward toward the central point, representing its gradual loss of energy until it comes to rest. A planet orbiting the sun traces out a perfect ellipse, endlessly repeating the same path through its phase space. These are examples of what mathematicians call attractors, geometric structures in phase space that represent the long-term behavior toward which systems evolve. But when Lorenz plotted his simplified weather equations in three-dimensional phase space, he discovered something unprecedented. The system's trajectory neither spiraled into a fixed point nor traced out a repeating loop. Instead, it wandered through space in an apparently random manner, yet remained, confined within a specific region. The resulting pattern looked like a butterfly with its wings spread wide, but this butterfly possessed properties that defied conventional geometric understanding. The Lorenz attractor, as this butterfly-shaped structure came to be known, represents a completely new category of mathematical object. Unlike the smooth curves and surfaces familiar from traditional geometry, the Lorenz attractor contains infinite detail at every scale of magnification. Zoom in on any portion of the butterfly's wing, and you'll find smaller copies of the same intricate structure. Zoom in further, and the pattern repeats again, revealing layers upon layers of self-similar complexity. This fractal nature means that the Lorentz attractor has a dimensionality that falls between traditional categories. It's more complex than a two-dimensional surface, but less space-filling than a three-dimensional volume. Mathematicians measure its dimension as approximately 2.06, a non-integer value that reflects its fractal geometry. This strange dimensionality is a signature of chaos, revealing systems that exist in the mathematical borderland between simple order and complete randomness. What makes the Lorentz attractor even more mysterious is how it manages to contain infinite complexity within finite boundaries. The butterfly-shaped region has definite limits. The system's trajectory never escapes to infinity. Yet within those boundaries, the path never exactly repeats itself. The system explores its allowed territory with infinite creativity, visiting some regions frequently and others rarely, but never tracing exactly the same route twice. This behavior emerges from the exquisite balance between two competing mathematical forces. The system is dissipative, meaning it loses energy over time, which tends to compress trajectories towards smaller regions of phase space. But it's also nonlinear, meaning small differences get amplified, which tends to spread trajectories apart. The interplay between these forces creates the strange attractor, a geometric structure that attracts nearby trajectories while simultaneously preventing them from settling into simple, repeating patterns. The discovery of strange attractors revealed that chaos possesses its own form of order, fundamentally different from the periodic order of pendulums and planets. Chaotic systems don't repeat exactly, but they do exhibit statistical regularities. The Lorentz attractor visits different regions of its butterfly wings with specific probabilities that remain constant over time. While you cannot predict exactly where the system will be at any future moment, you can calculate the likelihood of finding it in any particular region. This statistical order within chaos explains why weather patterns, despite being unpredictable in detail, follow seasonal trends and regional climates. The atmosphere's strange attractor ensures that certain types of weather are more probable than others in specific locations and times of year. The butterfly effect makes precise prediction impossible, but the underlying attractor preserves statistical predictability that allows us to understand climate patterns spanning decades or centuries. Strange attractors also explain how complex systems can maintain their identity while constantly changing. Your brain, your body's immune system, and the ecosystem in a forest all exhibit chaotic dynamics, yet they retain recognizable characteristics over time. They exist on strange attractors that preserve their essential structure while allowing infinite variation in detail. The attractor acts like a mathematical signature, a geometric fingerprint that defines what the system is while permitting endless exploration of what it might become. The mathematics of strange attractors reveals something profound about the relationship between determinism and creativity. These systems follow precise mathematical laws with no random elements whatsoever. Every trajectory is completely determined by the equations governing the system's evolution. Yet the resulting behavior appears creative, innovative, unpredictable. The system constantly generates new patterns and explores new possibilities, all while obeying rigid mathematical constraints. This insight transforms our understanding of natural creativity. Biological evolution, artistic inspiration, technological innovation, and even the emergence of consciousness itself might all emerge from dynamics similar to those governing strange attractors. Deterministic laws don't prevent creativity. They provide the framework within which creativity can flourish. The constraints imposed by mathematical necessity create rather than eliminate the possibility for genuine novelty. The geometry of strange attractors also reveals why chaos is so sensitive to initial conditions. Since the attractor contains infinite detail at every scale, trajectories that start arbitrarily close together will eventually explore different fine-scale features of the geometric structure. What begins as a microscopic difference in starting position grows into macroscopic differences in behavior as the trajectories navigate the fractal landscape of the attractor. This geometric perspective on sensitive dependence illuminates why the butterfly effect is inevitable in chaotic systems. It's not that the mathematics is approximate or that we lack sufficient precision in our measurements. It's that the underlying geometry of phase space contains infinite complexity that amplifies any uncertainty, no matter how small. The butterfly effect emerges naturally from the fractal structure of strange attractors. Modern research has revealed that strange attractors appear throughout nature, from the beating of human hearts, to the fluctuations of financial markets, to the dynamics of neural networks in the brain. Each system creates its own characteristic attractor, with unique geometric properties that reflect the underlying physics or biology. The human brain alone might contain millions of strange attractors corresponding to different patterns of neural activity, each one representing a different mode of consciousness or cognitive state. What Lorentz discovered in his simple three-equation weather model was actually a window into one of the universe's most fundamental organizing principles. Strange attractors represent the mathematical mechanism by which complex systems balance stability and change, preserving their essential character while remaining open to infinite possibility. They show us how deterministic laws can generate behavior that appears random, how mathematical constraints can enable rather than prevent creativity, and how the universe maintains coherent structure while constantly innovating. The butterfly-shaped Lorentz attractor isn't just a pretty mathematical pattern. It's a map of how chaos creates order, how simplicity generates complexity, and how the rigid laws of physics leave room for the endless improvisation that makes life, consciousness, and creativity possible. In the strange geometry of chaos, we find not mathematical chaos, but the deepest kind of mathematical beauty. Patterns that never repeat yet never lose their essential form. Systems that obey perfect laws yet never stop surprising us. Attractors that draw us toward understanding the infinite creativity hidden within the universe's most fundamental structures. Chapter 5: Quantum Chaos, where two worlds collide. In 1927, a German physicist named Werner Heisenberg discovered something that would make the butterfly effect even more profound and mysterious than Edward Lorenz could have imagined. Heisenberg proved that at the quantum level, the universe contains fundamental uncertainties that no measurement can eliminate. You cannot simultaneously know both the exact position and exact momentum of any particle. This isn't a limitation of our measuring instruments. It's a basic feature of reality itself. When quantum mechanics meets chaos theory, the result is a form of unpredictability so deep that it reaches into the very fabric of space and time. The marriage between quantum mechanics and chaos theory creates what physicists call quantum chaos, a realm where the strange world of atoms and electrons collides with the sensitive dependence on initial conditions that Lorentz discovered in weather systems. In this quantum realm, the butterfly effect doesn't just amplify tiny differences in starting conditions. It amplifies the fundamental uncertainties that exist at the heart of matter itself. To understand how profound this becomes, imagine trying to predict the motion of a single electron in an atom. Classical physics would tell us that if we could measure the electron's position and velocity with perfect precision, we could calculate its future path with mathematical certainty. But Heisenberg's uncertainty principle makes such precision impossible. The more accurately we measure the electron's position, the less accurately we can know its momentum, and vice versa. There's an irreducible fuzziness built into the quantum world that no technology can overcome. This quantum fuzziness might seem negligible on the scale of everyday objects. After all, the uncertainty in an electron's position is far smaller than the width of an atom. But when quantum systems exhibit chaotic dynamics, these microscopic uncertainties get amplified through the same mathematical mechanisms that turn tiny weather variations into massive storms. Quantum uncertainty becomes macroscopic unpredictability through the relentless magnification of chaotic amplification. The double-slit experiment, one of the most famous demonstrations in all of physics, reveals how quantum mechanics creates the perfect conditions for chaotic amplification. When we fire individual electrons at a barrier with two parallel slits, each electron somehow passes through both slits simultaneously, creating an interference pattern on the detector screen. But if we try to observe which slit the electron actually uses, the interference pattern disappears. The act of measurement changes the quantum system's behavior in unpredictable ways. Now imagine a chaotic system where the outcome depends sensitively on quantum measurements. The choice of whether to observe or not observe a quantum particle could determine whether the system evolves toward one strange attractor or another. The fundamental randomness of quantum measurement gets amplified by chaotic dynamics until microscopic quantum events influence macroscopic outcomes. A single photon's path through a double-slit apparatus could eventually determine whether a butterfly flaps its wings in Brazil or remains at rest. This quantum amplification explains why the butterfly effect extends far beyond classical mechanical systems. Every atom in the universe is governed by quantum mechanics, which means every atom contains irreducible uncertainties. When these atoms participate in chaotic systems, their quantum uncertainties become seeds for macroscopic unpredictability. The quantum world doesn't just allow for butterfly effects, it guarantees them. Quantum decoherence, the process by which quantum systems lose their strange quantum properties through interaction with their environment, provides another pathway for microscopic quantum events to influence macroscopic chaos. When a quantum system decoheres, it randomly collapses into one of many possible classical states. If that quantum system is part of a larger chaotic system, the random outcome of decoherence can send the entire system down a completely different evolutionary path. Consider a laser whose output depends on the quantum state of individual photons in its optical cavity. The laser's behavior exhibits chaotic dynamics, oscillating between different modes of operation in unpredictable ways. But the transitions between these modes depend on quantum events. The spontaneous emission of photons, the random absorption of background radiation, the quantum fluctuations of the electromagnetic field itself. These quantum events, amplified by the laser's chaotic dynamics, create macroscopic changes in the laser's output that ripple outward into the larger world. The human brain provides perhaps the most intriguing example of quantum chaos in action. Neural networks in the brain exhibit chaotic dynamics, with small changes in synaptic strength leading to dramatically different patterns of neural activity. But synaptic transmission itself depends on quantum mechanical processes. The tunneling of ions through protein channels, the quantum states of neurotransmitter molecules, the random thermal fluctuations that influence when neurons fire. Some researchers speculate that consciousness itself might emerge from quantum chaos in neural networks. The quantum uncertainties in individual synapses get amplified by the brain's chaotic dynamics, creating the unpredictable, creative, seemingly free patterns of thought that characterize conscious experience. In this view, every thought you think depends on quantum events in your brain that occurred nanoseconds earlier, events that were fundamentally random and unpredictable. Quantum chaos also appears in the behavior of individual atoms and molecules. When atoms absorb energy and become excited, their electrons can exhibit chaotic motion around the nucleus. The pathways these electrons follow depend sensitively on quantum initial conditions that cannot be precisely determined. Two atoms in apparently identical states can evolve in completely different ways because of quantum uncertainties, smaller than the wavelength of light. Chemical reactions provide another arena where quantum chaos plays a crucial role. The breaking and forming of chemical bonds depends on quantum tunneling effects that are inherently random. Whether a particular molecule reacts or remains stable can depend on quantum events that occur at the femtosecond timescale. In complex chemical systems exhibiting chaotic dynamics, these quantum scale decisions get amplified into macroscopic chemical behavior. The phenomenon of quantum scarring reveals how quantum mechanics can preserve classical chaotic structures in unexpected ways. In some quantum systems that correspond to classical chaotic systems, the quantum wave function concentrates along the paths that classical particles would follow in their chaotic motion. These quantum scars create bridges between the microscopic quantum world and the macroscopic classical world, allowing quantum uncertainties to influence classical chaotic trajectories. Perhaps the most mind-bending aspect of quantum chaos is how it affects the nature of measurement itself. When we try to measure a chaotic quantum system, the act of measurement not only reveals the system's state, but also influences its future evolution. The random collapse of the quantum wave function during measurement provides new sources of unpredictability that get amplified by chaotic dynamics. In quantum chaotic systems, the observer doesn't just observe reality, the observer participates in creating reality through the fundamental randomness of quantum measurement. This observer effect in quantum chaos means that the butterfly effect extends to include the choices made by conscious observers. Every time you decide to measure a quantum system, you introduce new sources of randomness that can cascade through chaotic amplification. Your decision to turn on a light switch doesn't just send electromagnetic radiation into space, it also triggers quantum measurements in photodetectors, solar cells, and biological molecules that can influence chaotic systems throughout the universe. The marriage of quantum mechanics and chaos theory also reveals new aspects of the relationship between information and physical reality. Quantum systems can exist in superposition states that contain more information than any classical measurement can extract. When these quantum systems participate in chaotic dynamics, the unmeasured quantum information can influence the system's evolution in ways that seem to violate classical causality. Information itself becomes a physical agent that shapes the evolution of chaotic systems. Recent experiments in quantum computing have demonstrated that quantum chaos can be harnessed to perform calculations that would be impossible with classical computers. Quantum algorithms exploit the sensitive dependence on initial conditions in quantum systems to explore vast solution spaces efficiently. The same mathematical mechanisms that make long-term prediction impossible in chaotic systems can be used to solve certain computational problems exponentially faster than any classical approach. The study of quantum chaos has also revealed fundamental connections between thermodynamics and information theory. In quantum chaotic systems, the arrow of time emerges from the amplification of quantum uncertainties into macroscopic irreversibility. The second law of thermodynamics, which describes the inevitable increase of entropy in isolated systems, can be understood as a consequence of quantum chaos, spreading information from microscopic scales to macroscopic scales. This perspective suggests that the butterfly effect isn't just a curious property of certain mathematical equations. It's a fundamental feature of how information flows through the universe, connecting quantum scale events to cosmic scale phenomena through the mathematical amplification of chaos. Every quantum measurement, every random quantum event, every collapse of a quantum wave function contributes to the ongoing creation of classical reality through chaotic dynamics. When we ask whether flipping a light switch can affect a distant star, quantum chaos provides a definitive answer. Not only can it affect distant stars, it must affect them. The quantum uncertainties triggered by turning on a light propagate through chaotic systems at every scale, from the molecular dynamics in the switch itself to the electromagnetic radiation that travels through space to the quantum processes in stellar atmospheres. The butterfly effect, amplified by quantum mechanics, ensures that every action reverberates through the universe in ways that connect the smallest scales to the largest, the most local events to the most distant consequences, the quantum realm to the cosmic realm in an endless dance of cause and effect that makes prediction impossible, but makes reality infinitely creative. Chapter 6. The Cosmic Cascade, from light switches to starlight. When you flip a light switch in your bedroom at 3 in the morning, you unleash a cascade of electromagnetic radiation that begins racing outward at the speed of light, carrying with it the potential to influence events throughout the observable universe. This isn't poetic metaphor. This is the stark reality of how energy propagates through space, according to the fundamental laws of physics. Every photon released by that incandescent bulb becomes a messenger carrying information about your nighttime decision to every corner of the cosmos, including binary star systems millions of light years away. The physics of this cosmic connection begins with Maxwell's equations, discovered in the 1860s by Scottish physicist James Clerk Maxwell. These elegant mathematical relationships describe how electric and magnetic fields create electromagnetic waves that propagate through empty space. When electrical current flows through the filament of your light bulb, it creates oscillating electromagnetic fields that generate streams of photons, each one carrying a tiny packet of energy outward at precisely 299,792,458 meters per second. According to the inverse square law, the intensity of electromagnetic radiation decreases as the square of the distance from its source. This means that if you double the distance from a light bulb, the brightness becomes 1/4 as intense. If you increase the distance by a factor of 10, the brightness drops to 1/100th of its original value. By the time your bedroom light's photons reach even the nearest star beyond our solar system, they have been diluted by a factor of approximately 10 to the 31st power. Yet, this astronomical dilution doesn't eliminate the influence entirely. It merely reduces it to levels that seem impossibly small by everyday standards. A single photon from your light switch, arriving at Alpha Centauri 4.3 years after you flip the switch, carries roughly 10 to the minus 23 watts of power. This is unimaginably faint, but it represents real energy that can, under the right circumstances, trigger measurable changes in physical systems. Modern gravitational wave detectors demonstrate just how sensitive physical measurements can become when we harness the principles of quantum mechanics and chaos theory. The Laser Interferometer, gravitational wave observatory known as LIGO, can detect changes in distance smaller than 1/10,000th the width of a proton. When gravitational waves from colliding black holes pass through Earth, they stretch and compress space itself by these incredibly tiny amounts. LIGO's lasers can measure these fluctuations because they amplify small signals through interferometry, using the wave nature of light to convert microscopic distance changes into measurable intensity variations. If human technology can detect such minuscule effects, imagine what might be possible with natural systems that have evolved over billions of years to respond to the faintest signals. Stellar atmospheres contain ionized gases where individual photons can trigger cascade reactions in plasma dynamics. A single high-energy photon striking a stellar atmosphere at just the right moment could initiate changes in magnetic field configurations that alter the star's entire electromagnetic behavior. The chaotic dynamics of stellar systems amplify these microscopic influences through the same mathematical mechanisms that create weather unpredictability on Earth. Binary star systems, where two stars orbit each other in gravitational dance, are particularly sensitive to small perturbations. The orbital mechanics of such systems can exhibit chaotic behavior, where tiny changes in gravitational influences accumulate over thousands of years into dramatic modifications of stellar orbits. Consider a binary star system where one star periodically passes close to its companion, creating tidal forces that trigger stellar flares and magnetic reconnection events. The timing of these close approaches depends sensitively on the precise orbital parameters of both stars. If the arrival of electromagnetic radiation from distant sources, including Earth-based light switches, slightly modifies the stellar atmospheres during critical moments, it could influence the timing and intensity of magnetic interactions between the two stars. Stellar magnetic fields provide the perfect mechanism for amplifying tiny electromagnetic disturbances into macroscopic changes. These magnetic fields, generated by convection currents in stellar interiors, can store enormous amounts of energy in twisted and compressed configurations. When magnetic field lines reconnect, they release this stored energy explosively, creating solar flares that dwarf the total energy output of human civilization. The triggers for magnetic reconnection can be surprisingly subtle, requiring only small perturbations to tip carefully balanced magnetic configurations into explosive release. Photons from your light switch arriving at a distant star could provide exactly such subtle triggers. If those photons arrive during a period when the stellar magnetic field is poised near a critical transition point, they could influence the timing of magnetic reconnection events. The resulting stellar flare might then alter the star's magnetic field configuration, which could affect its gravitational interactions with companion stars or orbiting planets. The three-body problem that tormented Newton provides another pathway for small influences to create large effects in stellar systems. Binary stars often exist within larger gravitational systems containing additional stars, planets, or dense interstellar matter. The gravitational interactions among these multiple bodies create chaotic dynamics where tiny perturbations can eventually lead to dramatic orbital changes. Electromagnetic radiation pressure, though incredibly weak, can exert measurable forces on stellar atmospheres over long time periods. This radiation pressure contributes to stellar winds, the continuous streams of charged particles that flow outward from stars. If electromagnetic radiation from Earth slightly modifies these stellar winds, it could alter the mass loss rate from the star, which gradually changes the star's gravitational mass and thereby influences its orbital dynamics in binary systems. The Yarkovsky effect demonstrates how even thermal radiation can create measurable orbital changes over astronomical timescales. This effect, first proposed in 1896, describes how asymmetric thermal emission from rotating objects creates tiny rocket-like forces that gradually modify their orbits. Asteroids in our solar system experience orbital drift due to the Yarkovsky effect, accumulating changes of several kilometers per million years. If thermal asymmetries in stellar atmospheres can be influenced by external electromagnetic radiation, similar effects might operate in binary star systems. The differential heating of stellar surfaces by electromagnetic waves from distant sources could create asymmetric thermal emission patterns that generate small but persistent forces. Over millions of years, these forces could accumulate into measurable changes in stellar orbits. Gravitational waves provide yet another mechanism for connecting local actions to distant stellar systems. When you flip a light switch, you accelerate electrical charges in the switch mechanism, and according to Einstein's general relativity, any accelerating mass creates gravitational waves. These waves are unimaginably weak for everyday objects, but they propagate through space at light speed, carrying information about your action to every gravitationally sensitive system in the universe. Binary star systems are particularly sensitive to gravitational wave influences, because their orbital dynamics involve precisely timed gravitational interactions. If gravitational waves from Earth arrive at critical moments during close stellar approaches, they could minutely modify the gravitational forces between the stars. Over many orbital cycles, these tiny modifications could accumulate into detectable changes in orbital parameters. The sensitivity of binary systems to external influences becomes even more pronounced when one of the stars is a compact object like a neutron star or white dwarf. These incredibly dense objects have such strong gravitational fields that small changes in their motion can create large changes in their electromagnetic emissions. Neutron stars with magnetic fields trillions of times stronger than Earth's can convert tiny orbital modifications into dramatic changes in their radio wave emissions. Some binary systems contain pulsars, neutron stars that emit regular beams of radio waves as they rotate. The timing of pulsar signals is so precise that astronomers use them as cosmic clocks, detecting orbital changes as small as parts per billion through accumulated timing shifts. If electromagnetic radiation from Earth influences the orbital dynamics of pulsar systems, those influences would eventually become detectable as systematic changes in pulse arrival times. The quantum mechanical nature of the electromagnetic radiation adds another layer of complexity to these cosmic connections. Individual photons from your light switch carry not just energy but also quantum information that can influence quantum states in distant stellar systems. When these photons interact with matter in stellar atmospheres, they can trigger quantum measurement events that randomly collapse quantum superposition states into specific classical outcomes. In stellar systems exhibiting chaotic dynamics, these quantum measurement events provide additional sources of randomness that get amplified through chaotic amplification. The quantum nature of light from your bedroom switch thus contributes to the fundamental unpredictability of stellar evolution, ensuring that even identical stars in identical environments will evolve differently due to quantum differences in the electromagnetic radiation they receive from throughout the universe. Interstellar dust clouds provide intermediate systems that can relay and amplify electromagnetic influences across vast distances. These clouds, containing complex molecules and charged particles, respond to electromagnetic radiation by heating, ionizing, and changing their optical properties. Modified dust clouds can alter the electromagnetic environment around nearby stellar systems, creating secondary effects that propagate the influence of your light switch across multiple star systems. The cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space, provides a reference frame against which all other electromagnetic radiation is measured. When photons from your light switch merge with this cosmic background, they slightly modify its local properties, creating tiny anisotropies that could influence the formation and evolution of structures in the early universe if we could somehow reverse the arrow of time. Perhaps most remarkably, the expanding universe itself amplifies the reach of electromagnetic influences through cosmological redshift. As space expands, it stretches the wavelengths of photons traveling through it, allowing radio waves from your light switch to eventually become cosmic background radiation that bathes the entire observable universe. In the deep cosmic future, electromagnetic waves generated by flipping light switches today will contribute to the thermal environment that influences the formation of new stars and galaxies. The butterfly effect in stellar systems reveals that we live in a universe where every action, no matter how small, participates in the ongoing evolution of cosmic structures. Your decision to illuminate your bedroom sends ripples through space and time that will continue propagating for billions of years, carrying information about that moment to the most distant reaches of the observable universe. The electromagnetic signature of your light switch will outlive our solar system, our galaxy, and perhaps even the current expansion phase of the universe itself, making every nighttime illumination a permanent contribution to the cosmic story. Chapter 7: The Human Element, Your Daily Actions in the Cosmic Web. Every morning, when 7 billion people wake up and step out of bed, they collectively alter Earth's rotation in ways that sensitive astronomical instruments can detect. This isn't theoretical physics or mathematical speculation. This is measurable reality. When the population of China simultaneously moves from their beds to upright positions during their morning routine, they redistribute enough mass to change Earth's moment of inertia, causing our planet to spin slightly faster for a few hours. Your individual contribution to this effect amounts to roughly 1 part in 10 to the 18th power. But in a chaotic universe where tiny causes can have vast effects, even your morning routine becomes part of the cosmic butterfly effect. The mathematics of rotational dynamics explains how human activities influence planetary motion through conservation of angular momentum. When you climb stairs, drive east or west, or even walk across your living room, you're redistributing mass relative to Earth's axis of rotation. These mass redistributions create tiny changes in how Earth's weight is distributed, which must be compensated by corresponding changes in rotational velocity to preserve total angular momentum. The planet responds to human activity like a figure skater pulling in her arms, spinning faster when mass moves closer to the rotation axis and slower when mass moves away. Modern satellite technology can measure these human-induced changes in Earth's rotation with extraordinary precision. The International Earth Rotation and Reference System Service monitors our planet's rotational variations using techniques that combine GPS measurements, laser ranging to satellites, and very long baseline interferometry with distant quasars. These measurements reveal that large-scale human activities, from seasonal migrations to major sporting events that synchronize the movements of millions of people, create detectable perturbations in Earth's rotation rate. But the butterfly effect amplifies these tiny rotational changes through atmospheric and oceanic dynamics. Earth's rotation influences wind patterns through the Coriolis effect, which deflects moving air masses to create the large-scale circulation patterns that drive global weather systems. When human activities modify Earth's rotation, they subtly alter these atmospheric circulation patterns. The changes are microscopic initially, but they propagate through the chaotic dynamics of weather systems, potentially influencing storm formation, rainfall patterns, and temperature distributions across the planet. Ocean currents provide another pathway for human-induced rotational changes to cascade through Earth's climate system. The rotation of the planet drives major ocean currents like the Gulf Stream and the Antarctic Circumpolar Current through geostrophic balance, where the Coriolis force balances pressure gradients in the water. Tiny changes in rotation rate can modify these delicate balances, potentially altering current speeds and directions in ways that influence marine ecosystems and regional climate patterns. The interconnectedness of Earth's climate system means that local weather changes triggered by rotational perturbations can propagate globally through atmospheric teleconnections. A subtle shift in storm tracks over the Pacific Ocean, caused by barely detectable changes in Earth's rotation, might influence the strength of El Niño events, which in turn affect rainfall patterns from California to Australia. Your morning walk to the mailbox contributes infinitesimally to this global chain of climate influences through its tiny effect on planetary rotation. Economic markets provide perhaps the most dramatic example of how individual human actions can cascade through complex systems to create massive global effects. Financial markets exhibit chaotic dynamics where small changes in investor sentiment can trigger avalanches of buying or selling that reshape entire economies. The mathematical models used to analyze market crashes reveal the same sensitive dependence on initial conditions that Edward Lorenz discovered in weather systems. Consider how a single social media post can trigger market volatility through the butterfly effect of modern communication networks. When one person shares news about a company, that information spreads through social networks according to mathematical principles similar to those governing epidemic spread. If the timing and content of the post coincide with existing market tensions, it can initiate cascading reactions that amplify into billions of dollars of market movement within hours. The 2008 financial crisis demonstrates how local events can cascade into global catastrophes through the interconnected nature of modern economic systems. Individual decisions by homeowners to default on mortgages in specific neighborhoods created ripple effects that propagated through complex financial instruments, eventually triggering bank failures and economic recession worldwide. Each individual default was a tiny perturbation, but the chaotic dynamics of financial markets amplified these perturbations into systemic collapse. Social media platforms have created new channels for butterfly effects to propagate through human society at unprecedented speeds. The algorithms that determine which content appears in news feeds exhibit chaotic sensitivity to user interactions. A single like, share, or comment can alter the trajectory of viral content spread, potentially influencing millions of people's opinions and behaviors. The mathematical models describing viral spread reveal power law distributions and phase transitions that mirror the behavior of chaotic physical systems. The Arab Spring uprisings of 2011 illustrate how individual actions in social networks can trigger massive political changes through chaotic amplification. The self-immolation of Mohamed Bouazizi, a fruit vendor in Tunisia, created a social media cascade that spread across the Middle East, toppling governments and reshaping the political landscape of entire regions. His individual act of protest became the initial condition for a chaotic social dynamical system that evolved in ways no one could have predicted. Urban traffic systems provide everyday examples of how individual driving decisions create emergent patterns through chaotic dynamics. Traffic flow exhibits phase transitions between free-flowing and congested states that depend sensitively on the density and behavior of individual vehicles. A single driver's decision to change lanes at a critical moment can trigger traffic jams that propagate backward through the traffic stream, eventually affecting thousands of other drivers and altering their arrival times at destinations throughout the city. The butterfly effect in urban systems extends beyond traffic to include energy consumption, waste generation, and resource distribution. Smart city technologies reveal how individual choices about when to use electricity, water, or transportation services create complex demand patterns that can either stabilize or destabilize urban infrastructure systems. The timing of your decision to charge your electric vehicle or run your dishwasher contributes to grid dynamics that influence power generation scheduling and potentially the stability of electrical networks serving millions of people. Biological systems within human social networks exhibit chaotic dynamics that amplify individual health decisions into collective epidemiological outcomes. The spread of infectious diseases follows mathematical models with chaotic properties where small changes in transmission rates or contact patterns can determine whether an outbreak remains localized or becomes a pandemic. Individual decisions about vaccination, social distancing, or travel create butterfly effects that influence the health outcomes of entire populations. The human immune system itself demonstrates chaotic amplification of molecular scale events into organismal scale health outcomes. Individual encounters with pathogens create cascading immune responses that can follow multiple pathways depending on the precise timing and context of the initial exposure. Your body's response to a single virus particle depends on chaotic processes at the cellular level that can determine whether you remain healthy or develop illness, which in turn influences your interactions with others and their health outcomes. Digital communication networks amplify human butterfly effects through the mathematical properties of network topology and information propagation. The internet exhibits scale-free network properties where a few highly connected nodes can dramatically influence information flow throughout the entire system. When individuals with many social connections share information, they can trigger cascades that reach millions of people within hours, potentially influencing everything from consumer behavior to political opinions. The phenomenon of trending topics on social media platforms demonstrates real-time butterfly effects in human communication systems. The algorithmic amplification of content creates positive feedback loops where early engagement with a post dramatically increases its visibility, leading to viral spread that can influence news coverage, political discourse, and cultural conversations. Your decision to engage with specific content contributes to these amplification cascades in ways that can reshape public attention and social priorities. Consumer behavior creates butterfly effects in global supply chains through the sensitive dependence of production and distribution systems on demand fluctuations. Individual purchasing decisions aggregate into market signals that influence manufacturing schedules, shipping routes, and resource allocation decisions across multiple industries. The chaotic nature of consumer demand means that small changes in individual preferences can propagate through supply networks to create shortages, surpluses, or logistical disruptions in distant locations. Educational and cultural transmission systems exhibit chaotic amplification of individual learning and teaching interactions into generational knowledge evolution. When a teacher explains a concept in a particular way, or when a student asks an unexpected question, these small pedagogical events can influence how knowledge is transmitted to future generations. The butterfly effect in education means that individual classroom interactions contribute to the long-term evolution of human understanding and cultural development. Environmental impact assessment reveals how individual lifestyle choices aggregate into collective effects that can tip ecological systems between different stable states. Ecosystems often exist near critical thresholds where small additional pressures can trigger phase transitions to dramatically different ecological configurations. Individual decisions about consumption, transportation, and resource use contribute to these cumulative pressures in ways that can determine whether ecosystems remain stable or collapse into alternative states. The psychology of decision-making itself exhibits chaotic properties where small differences in emotional state, recent experiences, or environmental context can lead to dramatically different choices. These individual decision cascades then propagate through social networks to influence collective behavior patterns. Your mood when making a seemingly insignificant choice can influence your interactions with others, potentially triggering chains of social influence that reshape community dynamics. Modern data analytics reveals how digital footprints from individual online activities create butterfly effects in algorithmic systems that influence everything from product recommendations to loan approvals to newsfeed content. Machine learning algorithms exhibit sensitive dependence on training data, meaning that individual user interactions contribute to algorithmic evolution in ways that can alter the digital experiences of millions of future users. The global nature of modern communication and transportation systems means that local butterfly effects can propagate worldwide within hours or days. A factory shutdown in one country can cascade through global supply chains to affect production and prices internationally. A cultural trend emerging in one city can spread through social media to influence fashion, music, and lifestyle choices on different continents. Individual actions in our interconnected world contribute to a global network of cascading influences that make every personal choice a participant in planetary scale dynamics. Perhaps most remarkably, the butterfly effect in human systems reveals that individual agency and collective outcomes are intimately connected through the mathematical principles of chaos theory. You are simultaneously an insignificant component in vast global systems and a crucial participant whose actions can influence the trajectory of civilization itself. Every choice you make sends ripples through the complex networks of human society, potentially contributing to innovations, movements, conflicts, or collaborations that reshape the future in ways that no amount of computational power could predict. In recognizing the butterfly effect in human systems, we discover that personal responsibility and collective transformation are two sides of the same mathematical reality. The same chaotic dynamics that make long-term social prediction impossible also ensure that individual actions matter more than intuition might suggest. In a world governed by butterfly effects, every person becomes a force of historical change. Every decision becomes a seed of social evolution, and every moment becomes an opportunity to participate consciously in the ongoing improvisation of human civilization. Chapter 8: The Paradox of Prediction in a Chaotic Universe. The discovery of chaos theory created a profound paradox that continues to puzzle scientists and philosophers today. If the universe operates according to precise mathematical laws, and if those laws make long-term prediction impossible, then what does it mean to have knowledge about the future? This question becomes even more perplexing when we realize that the act of making predictions can itself change what we're trying to predict, creating strange loops where knowledge transforms reality and reality transforms knowledge in an endless dance of mutual influence. In the 1980s, meteorologists responded to Edward Lorenz's discovery of sensitive dependence on initial conditions by abandoning single weather forecasts in favor of ensemble forecasting. Instead of trying to predict one specific future, they began calculating many possible futures based on slightly different starting conditions. Modern weather prediction centers run dozens of computer simulations simultaneously, each beginning with tiny variations in atmospheric measurements, then analyze the collection of results to estimate probabilities rather than certainties. This ensemble approach reveals something profound about prediction in chaotic systems. While we cannot determine exactly what will happen, we can often calculate the likelihood of different outcomes. The atmosphere's strange attractor ensures that certain types of weather patterns are more probable than others in specific locations and seasons. Chaos destroys precise prediction, but preserves statistical forecasting, allowing us to make useful statements about future possibilities even when exact outcomes remain unknowable. But ensemble forecasting introduces its own philosophical puzzles. When meteorologists predict a 30% chance of rain, what does that percentage actually mean? It doesn't mean that 30% of the sky will experience a rainfall. It means that in 30% of the possible futures calculated by their ensemble of simulations, significant precipitation occurs. The prediction refers not to a single reality, but to a distribution of potential realities, raising deep questions about the relationship between mathematical models and physical truth. The limits of supercomputers in predicting chaotic systems reveal fundamental constraints that no amount of technological advancement can overcome. Chaos imposes what mathematicians call fundamental prediction horizons. Absolute time limits beyond which no calculation, no matter how sophisticated, can provide useful information about system behavior. For weather, this horizon extends roughly 2 weeks into the future. For asteroid trajectories in the solar system, it might reach several million years. For molecular motion in gases, it often lasts only microseconds. These prediction horizons aren't failures of current technology. They represent mathematical necessities imposed by the nature of chaotic dynamics themselves. To predict a chaotic system beyond its fundamental horizon would require measuring initial conditions with infinite precision, which quantum mechanics proves impossible. Even if we could build computers with unlimited computational power, they could not extend prediction beyond the fundamental limits imposed by sensitive dependence on initial conditions. Strange loops emerge when prediction systems attempt to predict their own behavior, or when predictions influence the systems being predicted. Financial markets provide the most dramatic examples of these self-referential dynamics. When traders use mathematical models to predict market movements, their trading decisions based on those predictions can alter market behavior in ways that invalidate the original predictions. The market becomes partially dependent on the models used to predict it, creating feedback loops that generate new forms of unpredictability. Economic game theory reveals how prediction attempts can create self-defeating or self-fulfilling prophecies through the strategic behavior of intelligent agents. If a bank predicts that another bank will fail, and acts on that prediction by refusing to lend money, the withdrawal of credit might actually cause the predicted failure. The prediction becomes a causal agent in creating the reality it forecasted, transforming the predictor from passive observer to active participant in the system's evolution. Social systems exhibit particularly complex forms of self-referential prediction paradoxes. Political polling attempts to measure public opinion, but the publication of poll results can influence voter behavior and thereby change the very opinions being measured. Candidates alter their strategies based on polling data, voters shift their support based on perceived electability, and media coverage changes based on poll numbers. The polling system becomes entangled with a political system in ways that make it impossible to separate measurement from influence. Consciousness itself might represent the ultimate strange loop in prediction systems. When we try to predict our own future behavior, we create the peculiar situation where the predictor and the predicted system are identical. Self-awareness allows us to anticipate our own actions, but that anticipation can cause us to change our behavior, which invalidates the original prediction and requires new predictions that can again change our behavior. Free will might emerge from this recursive loop, where conscious prediction of self-behavior creates the possibility for choosing different behaviors than those predicted. The observer effect in quantum mechanics adds another layer of complexity to prediction paradoxes. When we attempt to measure a quantum system precisely enough to predict its future behavior, the measurement itself disturbs the system and introduces new uncertainties. The act of observation changes what we're trying to observe, making prediction both necessary for knowledge and destructive of the very information needed for accurate prediction. Quantum systems seem designed to frustrate any attempt at complete predictive control. Artificial intelligence systems create new forms of prediction paradoxes through machine learning algorithms that modify their own behavior based on prediction accuracy. When an AI system makes predictions about human behavior and humans learn about those predictions, they might change their behavior to either conform to or defy the AI's expectations. The AI then learns from these changes and updates its predictive models, which again influences human behavior, creating an ongoing co-evolution between artificial predictors and human decision makers. Despite these fundamental limits, some aspects of reality remain remarkably predictable even in the presence of chaos. Planetary orbits, while technically chaotic over very long timescales, remain stable and predictable for millions of years. Thermodynamic properties of gases, despite being composed of trillions of chaotically moving molecules, follow precise statistical laws. Conservation principles continue to hold even when individual trajectories become unpredictable. This suggests that the universe operates on multiple levels of description, with different prediction horizons at different scales. Microscopic chaos can coexist with macroscopic order. Quantum uncertainty can coexist with classical determinism. Short-term unpredictability can coexist with long-term statistical regularities. The butterfly effect doesn't eliminate all forms of prediction. It reveals which types of prediction are possible and which are forever beyond reach. The relationship between determinism and free will becomes particularly puzzling in light of chaotic dynamics. Classical determinism suggests that the future is already fixed by present conditions, leaving no room for genuine choice. But chaos theory reveals that deterministic systems can be fundamentally unpredictable, creating a form of effective indeterminism even when underlying laws are strictly deterministic. Perhaps free will emerges not from the absence of causation, but from the presence of chaotic amplification that makes the consequences of our choices inherently unknowable. Information theory provides new insights into the relationship between prediction and reality in chaotic systems. Chaotic dynamics can be understood as information processing systems that take simple initial conditions and generate complex outputs through repeated mathematical transformations. The unpredictability of chaos reflects the computational irreducibility of these transformations. There are no shortcuts to calculating the final result, except by running through all the intermediate steps. This computational perspective suggests that the universe itself might be the fastest possible computer for calculating its own future. Any prediction system that attempts to forecast cosmic evolution must necessarily be less complex than the universe itself, which limits its predictive power. The universe computes its own future through the physical processes of time evolution, making reality the ultimate simulation of reality that cannot be improved upon or accelerated. Quantum computing introduces new possibilities for prediction in chaotic systems by exploiting quantum superposition to explore multiple computational pathways simultaneously. Quantum algorithms might be able to extend prediction horizons in certain chaotic systems by utilizing quantum parallelism to sample larger regions of phase space. However, quantum decoherence ensures that these quantum advantages remain limited, and the fundamental unpredictability of chaos persists even in quantum computational systems. The philosophical implications of unpredictability in deterministic systems challenge traditional notions of causation and scientific explanation. If causes can have unpredictable effects, what does it mean to understand natural phenomena? Science has traditionally sought to explain events by identifying their causes, but chaos theory reveals that identical causes can lead to dramatically different effects. Scientific understanding might need to shift from explaining specific outcomes to characterizing the space of possible outcomes and their probabilities. Perhaps the most profound insight emerging from prediction paradoxes is that uncertainty and creativity are intimately connected. The same mathematical mechanisms that make long-term prediction impossible also enable genuine novelty and innovation. If the future were completely predictable, it would contain no surprises, no creativity, no evolution, no learning. The unpredictability of chaotic systems creates space for genuine emergence, where new patterns and possibilities can arise that were not contained in the initial conditions. This suggests that the butterfly effect represents not a failure of predictive science, but rather the universe's way of ensuring its own creative evolution. Mathematical laws provide the framework within which creativity operates, but they do not determine the specific content of that creativity. Deterministic chaos creates a universe that is simultaneously law-governed and open-ended, structured and innovative, predictable in its principles, but unpredictable in its manifestations. The recognition that prediction has fundamental limits might actually enhance rather than diminish human agency and responsibility. If the future were completely determined and predictable, our choices would be mere illusions with predetermined outcomes. But in a chaotic universe where small actions can have large consequences, and where outcomes remain genuinely uncertain, every choice becomes meaningful, every action becomes consequential, and every moment becomes an opportunity to participate in the ongoing creation of reality. Living with the paradox of prediction in a chaotic universe requires accepting that knowledge and ignorance, control and surrender, determinism and freedom are not opposites, but complementary aspects of a deeper truth about the nature of existence itself. We can understand the principles governing reality without being able to predict its specific manifestations. We can influence outcomes without being able to control them completely. We can act responsibly without knowing all the consequences of our actions. In embracing the beautiful uncertainty of chaos, we discover not the limits of human knowledge, but the infinite creativity that makes knowledge meaningful and action transformative. Chapter 9: Living with Beautiful Uncertainty. The discovery of chaos theory fundamentally transformed how we understand complexity, revealing that the most intricate and beautiful patterns in nature emerge not despite unpredictability, but because of it. Before Edward Lorenz stumbled upon sensitive dependence on initial conditions, scientists believed that complexity required complicated causes. Simple systems should produce simple behaviors, while complex behaviors implied complex underlying mechanisms. Chaos theory shattered this assumption, showing us that the richest, most varied, and most creative phenomena in the universe arise from the interplay between simple rules and infinite possibility. Consider the fractal geometry hidden within the Mandelbrot set, discovered by mathematician Benoit Mandelbrot in the 1970s. This mathematical object, generated by repeatedly applying a simple equation to complex numbers, creates patterns of infinite complexity and stunning beauty. Zooming into any region of the Mandelbrot set reveals new landscapes of mathematical artistry that never repeat yet never lose their essential character. The same equation that produces smooth, simple regions also generates intricate spirals, delicate filaments, and explosive burst patterns that rival any human artistic creation. What makes the Mandelbrot set so remarkable is that its infinite complexity emerges from the repetitive application of one of the simplest possible mathematical operations: squaring a number and adding a constant. This represents chaos theory's most profound insight: that repetitive processes, even when governed by elementary rules, can generate unlimited creativity when those rules exhibit non-linear dynamics. The universe doesn't need complicated laws to produce complicated outcomes. It needs simple laws with chaotic properties that amplify tiny variations into vast diversity. This principle extends throughout the natural world, explaining how biological evolution creates the incredible variety of life forms through the simple process of random mutation followed by natural selection. Each organism's genetic code represents a point in the vast space of possible DNA sequences, and evolutionary processes explore this space through chaotic dynamics, where small genetic changes can have dramatic effects on survival and reproduction. The butterfly effect in evolution ensures that life never stops exploring new possibilities, constantly generating innovations that could never be predicted from existing species. The unpredictability of evolutionary processes represents not a flaw in nature's design, but rather its greatest strength. If evolution were completely predictable, it would follow predetermined pathways toward optimal solutions, potentially creating perfect organisms, but eliminating the diversity that makes ecosystems resilient to environmental changes. Chaotic evolution produces apparent inefficiencies and surprising solutions that often prove advantageous when conditions change unexpectedly. Human creativity itself exhibits all the hallmarks of chaotic dynamics, where small inspirations can cascade through associative networks in the mind to produce breakthrough insights that revolutionize entire fields of knowledge. The moment when Johann Sebastian Bach first heard the mathematical relationships hidden within musical harmonies, or when Charles Darwin realized that species could transform through natural selection, or when Emmy Noether glimpsed the connection between symmetry and conservation, represents chaos theory in action within human consciousness. Artistic creation demonstrates how constraints paradoxically enhance, rather than limit, creative expression. Poets working within the rigid structure of sonnets often produce more innovative language than those with complete formal freedom. Jazz musicians improvising within established chord progressions create melodies that transcend what any individual could compose through pure planning. The mathematical constraints of musical scales, poetic meters, and artistic proportions provide the framework within which chaotic creativity can flourish. This relationship between constraints and creativity reveals a fundamental principle of chaotic systems. Limitations don't prevent innovation, they channel it into forms that can persist and propagate. Strange attractors in phase space represent mathematical constraints that allow chaotic systems to explore infinite possibilities while maintaining recognizable identity. Similarly, physical laws constrain natural processes in ways that enable rather than eliminate creative evolution. The positive aspects of unpredictability become especially apparent when we consider how chaotic systems respond to damage and disruption. Ecosystems exhibit remarkable resilience, precisely because their chaotic dynamics prevent them from becoming locked into rigid patterns that could be destroyed by environmental changes. When disturbances occur, chaotic ecological networks can reorganize themselves in unexpected ways, finding new equilibrium states that maintain essential functions while adapting to changed conditions. Human societies demonstrate similar chaotic resilience through their ability to self-organize in response to crises and challenges. Social networks exhibit scale-free properties where local innovations can rapidly propagate through the entire system, allowing communities to adapt to new circumstances through distributed problem-solving rather than centralized planning. The butterfly effect in social dynamics ensures that individual creativity can influence collective outcomes, making every person a potential catalyst for positive transformation. Personal transformation and healing often follow chaotic dynamics, where small changes in perspective or behavior can trigger profound shifts in life patterns. Psychological therapy works by introducing tiny perturbations into established mental and emotional patterns, allowing chaotic amplification to reorganize psychological systems around healthier attractors. The same sensitive dependence on initial conditions that makes prediction impossible also makes rapid positive change achievable through surprisingly small interventions. The recognition that small actions can have large consequences transforms how we understand personal responsibility and individual agency. In a linear world where effects are proportional to causes, individual actions might seem insignificant compared to vast social and environmental challenges. But in a chaotic world where butterfly effects operate at every scale, personal choices become powerful tools for influencing outcomes far beyond their apparent scope. This insight doesn't diminish the importance of collective action, but rather reveals how individual and collective transformation are intimately connected through the mathematics of chaos. Social movements arise when individual acts of courage or creativity cascade through social networks to inspire others, creating positive feedback loops that can rapidly shift cultural attitudes and institutional behaviors. The butterfly effect ensures that personal transformation and social transformation are two aspects of the same underlying dynamic. Environmental conservation provides compelling examples of how small positive actions can cascade into large beneficial outcomes through chaotic amplification. Individual decisions to reduce consumption, support sustainable practices, or protect local ecosystems contribute to larger patterns of environmental change that can tip ecological systems toward healthier states. The chaotic nature of environmental systems means that conservation efforts can have impacts far greater than their immediate scope. Economic systems demonstrate how positive butterfly effects can create virtuous cycles of innovation and prosperity. Small investments in education, research, or entrepreneurship can trigger cascading effects that transform entire industries and regions. The chaotic dynamics of technological development ensure that breakthrough innovations often emerge from unexpected directions, making every creative effort a potential catalyst for widespread beneficial change. The therapeutic implications of chaos theory extend beyond individual healing to encompass community and planetary well-being. Understanding that complex problems often have simple solutions that become apparent only through chaotic exploration encourages approaches to global challenges that emphasize experimentation, adaptation, and distributed innovation rather than rigid planning and centralized control. Chaotic systems often find solutions that linear thinking cannot anticipate. Finding meaning in uncertainty requires recognizing that unpredictability is not the enemy of purpose, but rather its essential foundation. If the universe were completely predictable, conscious beings would be unnecessary. The future would unfold mechanically without requiring awareness, choice, or creativity. The existence of consciousness itself suggests that unpredictability serves a cosmic purpose, making awareness a meaningful participant in, rather than merely an observer of universal evolution. The butterfly effect reveals that we live in a universe designed for participation rather than observation. Every conscious action contributes to the ongoing improvisation of reality, making each moment an opportunity to influence the trajectory of cosmic evolution. This participation doesn't require grand gestures or heroic efforts. It operates through the accumulated effect of countless small choices that cascade through chaotic dynamics to shape the future in ways that no amount of calculation could predict. Chaos theory also illuminates the relationship between scientific understanding and spiritual wisdom. The recognition that deterministic laws can produce unpredictable outcomes reconciles scientific materialism with traditions that emphasize mystery, transcendence, and the limits of rational analysis. Science reveals the universe to be far stranger and more wonderful than either pure materialism or pure spirituality alone could imagine. The mathematical beauty hidden within chaotic systems suggests that unpredictability itself possesses aesthetic and perhaps even moral dimensions. The strange attractors discovered in phase space exhibit symmetries and proportions that resonate with human artistic sensibilities, implying deep connections between mathematical truth, natural beauty, and conscious appreciation. Chaos creates art on scales from molecular to cosmic, making the universe itself a creative masterpiece in constant evolution. Perhaps most profoundly, accepting uncertainty as beautiful rather than threatening transforms our relationship with time and mortality. In a predictable universe, time would be merely the mechanical unfolding of predetermined patterns, making each moment redundant with every other. But in a chaotic universe, time becomes creative, with each moment containing genuinely new possibilities that could not be anticipated from any previous moment. This makes every instant precious as a unique contribution to cosmic creativity. The butterfly effect thus reveals death not as the termination of individual significance, but as the completion of each person's unique contribution to universal evolution. Every life represents an unrepeatable exploration of consciousness and creativity that leaves permanent traces in the ongoing improvisation of reality. Individual mortality becomes meaningful within the context of collective immortality, where personal contributions cascade through chaotic dynamics to influence outcomes across cosmic timescales. Living with beautiful uncertainty means embracing our role as conscious participants in the universe's creative self-exploration. We are neither passive victims of random forces, nor omnipotent controllers of cosmic destiny. We are improvising musicians in a vast orchestra where our individual melodies interact with countless others through chaotic dynamics to create symphonies of complexity and beauty that transcend what any single consciousness could compose alone. The wisdom hidden within chaos theory is that uncertainty is not a problem to be solved, but a gift to be cherished. Unpredictability creates space for genuine surprise, authentic creativity, and meaningful choice. In accepting the beautiful uncertainty of existence, we discover that we live in a universe where love matters, where consciousness serves a purpose, where individual actions contribute to collective transformation, and where every moment contains infinite possibility for creating something genuinely new under the sun. This recognition transforms anxiety about the future into excitement about participation in cosmic creativity. We cannot predict what will happen, but we can trust that what happens will emerge from the ongoing interaction between mathematical necessity and conscious choice, between natural law and creative freedom, between individual agency and collective wisdom. In the beautiful uncertainty of chaos, we find not answers to all our questions, but something far more valuable. The assurance that questions themselves serve the universe's endless quest to understand and transform itself through the miracle of conscious awareness, participating in the eternal dance of cause and effect that connects every action to every other action across all scales of space and time.